welcome everybody to Professor Uwe Schlink's lecture tonight, public lecture, and welcome to Ustinov College, and thanks so much to Professor Glenn McGregor, who's the master of this college, and to all the staff who are not here but who are going to help us with drinks afterwards.
Is it too dark?
I think that'll be all right once we're there. So my name is Karen Johnson, and I am a Director for Science at the Institute of Advanced Studies. And it's the Institute of Advanced Studies, which is on Palace Green next to the cathedral, which is hosting Uwe. And you might not have heard of the IAS, some of you I know have, but the IAS Institute of Advanced Studies is one of 10 institutes at Durham, but what makes us unique is that we are the home for Durham, where we grow big ideas, basically. So if you've got an interdisciplinary idea, then we can take it and use a four-faculty approach to throw different people at you from the different faculties, different disciplines, to help you, to help provide scrutiny and creativity to get that idea right, so that you can put in a nice grant to carry out your research. So Uwe has a list as long as my arm of papers and all sorts of things, but he is from Leipzig Helmholtz Environmental Institute, and he is there leading a team of interdisciplinary researchers looking at the effects of heat in cities. But he didn't start off necessarily being an interdisciplinarian. He started off being a physicist and then a meteorologist. And then he spent a lot of time working in epidemiology, looking at the effects of environmental contaminants on the health of children. And all of this led him, anyway, to the Helmholtz Environmental Institute, which is, I hadn't heard of them, but they've found like a fantastic range of organizations, a bit like, for me as a scientist, the Max Planck Institutes in Germany, and particularly host this sort of interdisciplinary work, which Uwe is going to tell us about tonight. So the talk is basically about his work looking at air pollution in, actually, is it in Leipzig that you're carrying out?
It's an international
venture with many colleagues. Of course, because of global warming, cities are going to have to adapt to the heat and the effects of climate change. So at a major scale, we're going to have to adapt, we're going to have to change infrastructure, but at a personal level as well. This is where Uwe is combining interdisciplinarity by working with a social scientist to look at personal behavior of individuals and how we might adapt, walking about cities, cycling through cities, traveling through cities, in order to mitigate or adapt rather to the effects of heat. So I think I've said enough. I'm very much looking forward to hearing this talk, Uwe, and we'll have plenty of time for questions afterwards and a small glass of wine. Thanks.
Thank you very much, Karen, for the kind introduction. I just would like to add a short remark on this Helmholtz Institute issue. Max Planck Institutes are, I think, well known from Germany, but similar to Max Planck, in this group we have Max Planck. We also have research institutes Fraunhofer and Leibniz and also Helmholtz. So these are four different research organizations. Just that you have an impression how this is organized. And first of all, I would like to thank the Ustinov College and the IAS for inviting me and for giving me the opportunity to present our perspectives on climate change adaptation, and I hope it is working. Yes. So today I will speak about adaptation, and my focus here is on urban heat and pollutions like air and noise. And triggered by the global warming, cities are increasingly suffering from heat. And while air pollution and noise are very common environmental hazards in megacities, especially in developing countries, heat became a very pressing problem, especially in Europe, and this has been a matter of public awareness during the recent years. We urgently need to stabilize the climate by reducing greenhouse gas emissions, but not all consequences of climate change can be averted by mitigation. That is why adaptation is also necessary. So the development of adaptation techniques is the topic of my work and also of my presentation today. And we have, on the one hand, we have mitigation, and on the other hand, we have adaptation. They are both sides of the same coin, and together they are the climate action. So my question today will be, what are the drivers of urban heat? And as an answer, in the first part of my lecture, I will present modeling techniques, and they demonstrate the formation of urban temperature fields, and these techniques can help urban planners to develop strategies for the adaptation of the cities. And in the second part of my lecture, I will deal with the perceptions and the behavior of the people. So I try to make a bridge between the city and the people. Here on the right-hand side, you can see a photograph of our visualization lab, where we discuss different scenarios with stakeholders. People here can wear such glasses to have a three-dimensional view, and we compare and discuss specific policy-oriented research questions to improve the resilience of cities against climate change. For example, how to reduce the heat through a modification of urban green infrastructure. As an introduction, I would like to discuss with you how urban structure affects the local climate conditions in detail, and for that purpose I have here some examples. This is my first example, and it's a lane in Singapore, and there's no vegetation here. Although Singapore is otherwise known for its wealth of vegetation in the city, you have many, many trees. But this is very extreme here. All the materials are replaced, the natural materials are replaced by concrete, and the surface is sealed. And this radically alters the balances of water and also of energy. And how does this particular urban structure affect the thermal conditions? We see that there is no evaporation and no transpiration because there is no water available. The ventilation is strongly reduced due to this narrow lane here. And we have additional emissions of heat by these air conditioning devices. This picture here is a busy street in Cairo, in Egypt, and here crowds intermingle with cars and buses and motorbikes, and each of these units emits and injects heat and moisture and noise and creates a host of air pollutants and puts this into the urban canopy layer. The urban canopy layer is the atmosphere here in the street canyon below the level of the roofs. And this street canyon confines the airflow and restricts the dilution of the air pollutants. Although air pollution is not confined to cities, the density and the complex emission sources there and the proximity to large populations mean that it has a very particular relevance here in cities. Urban air pollution is a subject with a very length and extensive history. The London smog in 1952 is well known. And nowadays, other regions outside Europe suffer much more from poor air quality. But some types of the smog can be you can smell them, but others cannot be perceived, such as the photochemical smog, ozone, nitrogen oxides, hydrocarbons. And for these types of smog, people have no way to protect themselves because they don't realize that there's such smog. My third example is Marrakesh. And you see that the sunlight is basically reflected from this surface due to the light-colored rooftops. And less obvious from this picture here, but not visible, but equally important, are the infrared radiation exchanges among the buildings, here between the buildings, and between this urban surface and the atmosphere. This typically built structure minimizes the exposure of the walls of the buildings to the sun, and also the streets are in the shadow, and so this creates shaded spaces for the pedestrians and also for outdoor markets. At the surface, at any point within the urban canopy layer, the sky view factor is strongly reduced. What is a sky view factor? A sky view factor is the percentage of the sky that you can see from a location when you look to the sky, and you can see that the silhouette of these buildings reduces the sky view factor, and in the same way it affects the radiation budget for this point where you are. So my example here illustrates that the surface structure and the orientation to the sun and to the open sky and also the radiative properties, here the albedo of these buildings, this is important to understand the urban radiation exchanges. And it is not surprising that managing these radiation exchanges through building and landscape design is one of the most important tools available to architects and urban designers and landscape planners to control the microclimate in this area. My next example is a region here in my hometown, in Leipzig. Such parks are important places for well-being, for recreation. And here we can see that firstly, the shade is reduced. The shade reduces the solar radiation here below the trees. And the second is that the open space allows for good ventilation. And the third point is that the vegetation contributes to evaporative cooling. We know that the vegetation is an important factor influencing urban heat, and the local climate regulation provided by the green is a kind of ecosystem service. However, an important precondition is that the vegetation has sufficient water available. As you can see here, those dried out lawns, and although when the bushes are dry and the trees, and then they cannot contribute any cooling. So no water, no ecosystem service. Here in this example you see the campus of the Helwan University near Cairo in Egypt. And all buildings have special features. These are vertically open slots here that allow for good ventilation, and many buildings are surrounded by vegetation. In general, this architecture was intentionally designed to attenuate the heat. The microclimate results from the interaction between the atmospheric conditions in the region and also with this interaction with the local building structure. And that's why the air temperature in this area is not constant, but it fluctuates at very small spatial scale from place to place. Later, I will take this example and show you how strong the influence of the local land use elements is. And our question will be how much thermal protection can be achieved through an appropriate urban planning. This is an example in Berlin, the Danziger Straße. On the left-hand side, you see the current view of the Danziger Straße, and here on the right-hand side, you see a green vision of the same place. So they put some trees here and some grass and so, and this looks quite nice. But my question is, what is the detailed impact of more urban green on heat? how much additional green makes sense. Should we plant many trees here, or should we plant only few, and what types of trees, lime trees or oaks, or what is the best for a very good climate regulation. And we will discuss this now in the first part of my lecture, after this introduction. And these changes in the urban structure contribute to the long-term adaptation of cities. That is addressed by the city planners. But how can adaptation be achieved in the short term? And in the short term, the urban environment is perceived by each person, and everyone can in turn influence her or his personal exposure through their behavior. People's protective behavior can mitigate the exposure, and this applies to heat as well as to air pollution and to noise. People who move in or stay here in the green, like you see on the right-hand side, and they avoid busy roads, like here on the left-hand side, they can significantly reduce their direct exposure, and this protects against adverse health effects. The photo shows a volunteer here, both show a volunteer analyzing the effects of such an adaptive behavior. And in the second part of my talk, I will speak about our behavioral study. Urban climate conditions can be studied by combining such measurements. I just note that this lady here is wearing a sensor, and I will explain something more later in the second part about these wearable sensors. And so the urban conditions can be studied by these measurements and also by urban simulations. And for that purpose, I think we should speak about urban climate models and how they work. And this is the structure of a micrometeorological model having 3 dimensions, two vertical and 1 horizontal. And the area that is considered here, this is gridded in such grid cells, so we can explicitly model everything in this area in 3 dimensions. At the border of the model, you see it on the left-hand side here. At the border, there is a 1-dimensional model representing the vertical profile of the inflow of air. This specifies the vertical profile of temperature, humidity, and wind. And these data we can achieve from a weather station that is nearby, or by a regional weather model, or also by some regional climate projections to see how this reacts, or this might react in future. This scheme gives an idea about the basic structure of the model. We have here the input files on the left-hand side, then the simulation software, we have the output data, and we have some software for the visualization. On the input side, there are 3 main components. This part here represents the data of the area, how this is organized in the space, and you can get this data from 3-dimensional urban data from digital urban models, and that they are available for many cities, or very often from OpenStreetMap. You can just download this data, and all the urban data are very often combined in a so-called digital twin. This is a very modern to store the structure of urban areas. Here in the configuration file, this data involves the weather data. And here is a general database, and this contains the parameters of the materials, of the ground materials, of the building materials. And also it contains information of the specific types of vegetation. For example, this tool here specifies all the details of a tree. This is a tree, and we can design this tree by means of the characteristic traits that can be fixed here. And for example, the leaf area density or the root area density or the albedo of this tree or the metabolic pathway for carbon fixation in photosynthesis and so on. And it is possible to predefine different types of trees like an oak tree or like a pine tree, and then later these trees can be located in the area here of that should be modeled. So then we have the buildings here and we have some trees, and so we can prepare everything in detail. And when we apply such an urban climate model with all this three-dimensional data, this results in simulations of the atmospheric parameters, temperature, humidity, wind flow, air quality. And these parameters can be visualized in 3 dimensions here. And this is very fruitful for discussions with planners, stakeholders, and investors. How to start this here. So you see here this area with the buildings, and these are the streamlines of the wind here, and the color on the ground is either the temperature of the ground, of the surface, or also temperature differences. You can plot everything you want here. And in the following, I would like to present an example. A very interesting question is to make scenarios ex post ex ante. We have an area that should be rebuilt or revitalized, and we have a plan for new buildings, and the question is, what will be the effect of the new buildings? And this is our example. In Leipzig there are many brownfields. There have been many brownfields, and this area here is called the Bayerischer Bahnhof. It was a former train station here at the top of this stripe, and now this is revitalized step by step, and there was an urban planning concept. You see here some drafts developed, and the question was what is the impact of the new buildings on the spatial temperature distribution. And so we calculated our simulations 2 times, one just with the old buildings. The old buildings are here in black. This is from top a map of this area. And then again, the same with the new buildings included. The new buildings are here, the gray ones. And then we calculated the difference for each hour, the temperature difference, and this is the result here. This difference is not very high. It's around 1 degrees, but as we expected here in this area that is rebuilt, the temperature goes up a little. It's some warming here, but surprisingly, here in this area it becomes cooler due to these new buildings. And I have to mention that this is downstream. The wind comes from east here. So in the lee of the new buildings, there's some cooling. And it's difficult to understand this. But the three-dimensional visualization helps a lot. And this is a plot of the streamlines here. This is a new building, and you see that the new building directs the airflow upwards so that it passes this area in the height, and near the ground it stays cooler until noon. For a more comprehensive understanding of the formation of these urban temperatures, we now discuss the drivers of the urban heat. The temperatures in cities are mostly elevated in comparison to the surrounding area, and we call this urban heat island effect. And in the introduction, we discussed several real-world examples of such an urban overheating. And from these considerations, we conclude that there are at least 4 important drivers to urban heat. And they are referred to as biophysical factors. And these are the radiation budget, the convection, so this is the ventilation and the turbulent transport of heat in the atmosphere, the evapotranspiration, and also the storage of heat in the pavement, in the asphalt, and also in the walls of the buildings. This is also a biophysical factor that contributes to the heat. And we have developed a new algorithm to decompose the excess temperatures in an urban area into these 4 contributions. So for each of these biophysical factors, you now see a map here. And you see that it's very diverse, very different. And the color indicates the temperature. This delta T is always meant in comparison to the rural state. And you see this varies between -10 and +10 degrees. So each factor has a very typical pattern here. It is quite easy to decompose the heat balance, because from the simulation model you get all the heat fluxes at each point, but it is more complicated to decompose the temperature values, because then you need also the climate sensitivity of each pixel here, and this needs to be included. So an adaptation to climate change is always a local action. And so to see how this works, we consider a schoolyard that is here in this area. And here we can, this is the schoolyard. And yes, here we have the decomposition of the contributions to the temperature. And the schoolyard is very, like you can see, a very open place. And this is heated by strong sunlight. And for that reason, the contribution of the sunlight is 1 or 2 degrees. And it has very little greenery, so there's nearly no evapotranspiration. This results also in elevation of the temperature. But this area is very free and is very well ventilated, and this cools down by about 6 degrees. So to mitigate heat in the sun is positive, so it is overheated. And to mitigate the heat, we might consider improving the green infrastructure in this area. And we might consider planting many trees there. That it's very dense with green in this area. And then the contribution change as follows. We have the trees here, and I switch forward and backward. So the sun is reduced, the contribution of the sunshine is lower. Now we have more evaporation than before, so the evaporation cools down. But there is an adverse effect because the dense trees, they reduce the ventilation. And here the ventilation was cooling, but here there's no cooling. In contrast, it heats up. So this is a very surprising result, and this demonstrates that it is very important to find a good compromise between these biophysical factors, and our tool makes it possible to make an assessment prior to any changes of the real urban built structure. We observed another interesting and strong contribution to urban heat, that is the storage of heat in the surface materials. And for that reason, surface materials have a high potential to make a city resilient against heat. And this also includes the wetness of the urban surface, because water changes the heat capacity and also the heat conductivity of the surface. And when you have water, then also the evaporation will have a stronger effect. So we summarize that the modification of the biophysical factors has to be made in a very intelligent way, and this also needs to be tailored to each part of the city, to each quarter, to each neighborhood. And this technique can be very helpful for the creation of cool islands in cities. These cool islands can be used by the city dwellers. Imagine that you go for shopping and it's very hot, and when there's such a cool island, you can have a rest there, and this is very comfortable. Nevertheless, even this advanced procedure will have its limitations, and we ask how much of the variability of heat in urban areas can be influenced by the urban structure, by the land use. And for that purpose, we studied the heat patterns in one of my previous examples at the campus of the Helwan University in Cairo. It is near the Nile River, between the river and the Mokattam Hills, and about 24 kilometers south of Cairo. And this campus was established in 1975. And all buildings have designed to guarantee good ventilation and shadow as much as possible. And so this deliberately and purposefully designed area is this is also in a very hot climate, and this is a very ideal situation for answering the question of how this landscape architecture can affect thermal condition, how much, what is the effect of the landscape. As the microclimate results from the interaction of the atmospheric conditions in the region with the local urban structure or land use. For that reason, the air temperature is not constant, but it follows temporal modes and spatial patterns. So it has some typical patterns, and pattern recognition is a very interesting application here. And here you see our simulations of the temperature. Here the white spots are the buildings. Now they are white, not black. And this is the temperature at midnight, and then at different times you have different temperature distributions. And it was quite a hot day, and but anyway, you see the daily course that during the noon temperature goes up, and for that reason we identified the temporal pattern. What is the daily cycle? And the principal components analysis resulted in four typical patterns. The first one is the daily cycle, and the second one is a pattern that forms in the afternoon, in the early afternoon, due to some local circulations, due to the heating in the city. And both together, the first and the second pattern are together 97% of the heat variability. So we neglect all higher modes and just took these two, and then we reduced this temporal pattern from all the data. And after this, we have data that just have spatial variability. And we again applied here a principal components analysis, and we found four clear patterns. And these patterns are the anomalies. So they are the differences to the average value. So we see that they are very, very clear patterns, and the first one represents 81% of the variability, and the second one 13%. Together they have 94%, and we neglect these two, and we try to interpret these two patterns. And for that purpose we calculated the associations to on the one hand, to the atmospheric parameters. This is wind, humidity, turbulences in the atmosphere, and long-wave radiation. And the other block we studied are the land use parameters, the trees, the hedges, the coverage of the ground. And for that purpose we used hierarchical partitioning, because this has the advantage that we clearly can see how much variability in the temperature anomaly is explained by these variables. And here we see that the first pattern is clearly explained to 68% by the atmospheric parameters and only to about 30% by the land use. And this pattern is more explained by the land use. For that reason, we can interpret this as the atmospheric, the pattern due to the weather situation, and this is a pattern due to the land use. And as a consequence, we should recognize that this is only 13% of the temperature variability. So only 13% of the temperature variability can be attributed to the land use. So this clearly demonstrates that there are limits when we try to influence the heat patterns by changing land use. It's clear when you are in a desert area, subtropical area, you cannot create a fridge just by land use. It's clear, I think. So in summary, we saw that the biophysical factors are important for the formation of urban heat. Adaptation has to balance these factors, but the possibilities for adaptation through land use change and urban redevelopment are limited. To be honest, a weakness of our considerations here is that we so far neglected the contribution of anthropogenic heat. I think you had a very interesting publication about this. And depending on the city, this can have a very significant amount when you have many air conditioning devices and you have a lot of input of heat into the city. We did not include this here because our micrometeorological simulations are so far not able to take anthropogenic heat emissions into account. We discussed with other colleagues who implemented these models and who are more experts in this programming of these models, but they told us it's just in progress, but it's at the moment not possible. But we have this in mind, and in January a PhD student will come and start his project on anthropogenic heat assessment, at least an assessment from data from inventories and also from remote sensing data. And we hope that this can complete our approach. And now we are at the point that we are building a bridge from the city or from the quarter level to the people who live in the cities. How are heat and air quality perceived by the people living in the city? And how is this urban situation reflected at the scale of the individuals? In the following, I would like to discuss the assessment of the so-called personal exposure here. And personal exposure, I have to emphasize this, that personal exposure is not identical with the air pollution or the temperature fields we discussed in the first part. These fields represent the spatial and temporal distribution of temperature, pollutants, or anything, or noise. But personal exposure is when you consider the pollutants or the heat from the perspective of a receptor. So this is a totally different concept. And for this purpose, we apply person-based sensors like this, and this you can carry this with you, and we call them wearable sensors. Due to the technical development, such wearable sensors, there are many wearable sensors, many trackers, for example, health trackers, fitness trackers, and they mainly record physiological parameters of the people. But here we focus on tracking environmental parameters. So I think it's also clear that the exposure that is measured here is not only related to the local conditions, but also to the behavior of the individual. And this is a very, it's a new aspect of these considerations. So we see that the person-based measurements are useful for different purposes. Firstly, we can assess the cumulative burden of an individual. So this represents the risk that is relevant for the person's health and the well-being. So this is the individual-based view. On the other hand, the combination of the measurements with the GPS data for many persons provides a very good exploration of the urban environment, because people move everywhere in the city. And here on the top you see a result of the noise recordings taken in our study. And thirdly, this one, we can plot the data in 3 dimensions. This is an example of some of our results here in the city, where the people move and every ball here represents a measurement. But in contrast to this plot, another space-time world can be created, and this is called the time geography. This new plot considers the two-dimensional plane of the city, and the time here forms the vertical dimension. And when an individual moves in the city during the time, then the trajectories go up like this. And for sure, during the movement, the individual is exposed to different risk factors, and also these risk factors change with time. And this new plot represents a new concept that has been introduced in environmental epidemiology during the last 10 years. And this means that in each individual, the genome, the genetic information is supplemented by the so-called exposome. And this exposome comprises the totality of all environmental influences. And both genome and exposome are now used for investigations of associations of environmental conditions with diseases. And following this exposome approach, here we try to measure a set of exposure components, not all, sure, just some, along the daily life history of individuals. The next slide demonstrates how this sensing is made in our studies. Here is a volunteer. This is my colleague Caroline, and she carries a set of sensors here on the back. You will later see this. And this is a self-made, from our first measurement campaign, a self-made sensor set where we compose this from different types of sensors. And she also has on the left arm, it's difficult to see here, she has a smartphone here, and this smartphone collects all the data and also measures the movement by accelerometry and also the GPS position, and it stores the data and sends them to the database. And since 2021, we use a commercial, very compact sensor. Unfortunately, I forgot it today. I brought it to the seminar, but you saw it on the picture before. And this is produced by a small company near Cambridge. And this involves all the sensors in one, perfectly in one device. And this also provides the data processing and delivers all the data immediately to our database. And a surveillance of heat-related symptoms together with such exposure measurements is urgently needed, and especially for vulnerable population groups. Unfortunately, so far we have not yet been able to combine our measurements with health data. Just this summer we started a collaboration with colleagues running an epidemiological study that looks at adverse health effects in children. So the children are 14, 15 years old, and we now equip them with the sensors, and we are still in the process of data collection. However, we have considered other applications of these sensors, and I would like to shortly report about this. One possibility is to combine these measurements with the simulations I explained before with the urban climate models. And this is called data assimilation, and is a common technique in hemispheric scale weather forecasting. But for urban temperature data, this is not yet developed, and so I think this is a very interesting field that we can follow. I will show you an example in a minute. A second extension of these measurements is that an interviewer accompanies the volunteers and makes walking interviews about the perceptions and the opinions about the exposure. And the third possibility is that the measurements are used to provide feedback to the volunteers, recommend alternative routes, and we will consider how the behavior of the people changes. Just some words to each of these points. Here you see a simulation for an area in Leipzig. We have a residential area here, and this is a park area here above, and we have a small forest and meadows. And for that reason it is very interesting, because you have the contrast between the hot residential area and the cool park. And we took measurements in this area and also the simulation, and then we combined both by means of a statistical Bayesian algorithm. And this combination provides an interpolation of the data, because here between these measurement points you have no data normally, but when you combine both you have the data everywhere. And this procedure also filters the outliers and the fluctuations of the measurements. And as a byproduct of this technique, you also receive, you also get the uncertainties of this here. these are the uncertain. You see that especially at places where measurements were taken, sometimes uncertainty is very, very small, so these values are very correct and they agree to the simulation, but here uncertainties are a bit larger. And such heat maps, like this one, may contribute to an urban heat warning system, and this can be relevant for vulnerable people. And it indicates also cool islands. For example, here in this area, it's much cooler than here in this residential area. And this is due to some airflow in this region. And it might be involved in a warning application, for example, on a smartphone, and give people the opportunity to adapt their activities to the outdoor thermal conditions. This is an example of the walking interviews. It was carried out in Chennai, in India. Here the PhD student worked with volunteers. The volunteers were students from the Indian Institute of Technology in Chennai, and she accompanied them and asked for their perceptions and for their opinions, and the perceptions were coded at a Likert scale, and there are also some qualitative statements, and as a result of this study, we proposed that these perceptions of the volunteers form additional dimensions of the personal exposure. When you have the personal exposure as maybe heat, air pollution, noise, but then you also have the perceived heat, the perceived air pollution, the perceived noise, because this can strongly differ from the measured value. For example, when you have some green around you, then you have a very different perception. And to characterize the exposure of the individual more comprehensively, we should bring them together. And this approach also tries to combine the portable or mobile measurements with some ethnographic methods, and with the purpose to explore the exposure situation and the perceptions of the individuals, as well as their motivation to protect themselves. And this behavior, this protection behavior, is precisely that what is being looked at in our current study together with psychologists. And in this study we considered the feedback. We give the study participants a feedback on their exposure. So all the data here from this new sensor are displayed on the smartphone screen, and people normally have a start and they have a destination on their daily agenda or daily route, and you see the measurements here. In this example, they are mostly green and fine, but some of them are more yellow and more problematic. And in the end, the algorithm suggests a new route for the next day that is less polluted. So every week we recruited new groups of volunteers by means of publications in the local press, in Facebook, mailing lists, and via cycling clubs. And this application of the sensors was focused only on cyclists and pedestrians. And in our campaign, we worked with two groups. Each group contained 10 volunteers, and one group was equipped with a sensor, and the other group did not have the sensor. And this is the timetable, and they completed here a questionnaire, and then they received the sensor, and they measured, and they gave them the sensor, the device back, and then here they completed another survey, and they received some feedback, and another survey, and again another survey. And these 4 surveys are meant to see how they change their behavior and whether this is sustainable or not. Because this was 2 months after the period. And the control group did not have the sensor, but just filled in the surveys. And our question was, can individualized exposure feedback raise the awareness, and can it motivate the protection behavior? For that purpose, we measured in the survey the threat appraisal at a 7-point Likert scale. We had several items in the survey, and in result, interestingly, it was not significantly different between the measurement and the control group. So this is the threat appraisal, this is the 7-point Likert scale here, and this is for the measurement group, and this is for the control group. And statistically, there's no significant difference, but there's a significant effect with time. So the threat appraisal increased with the measurement, with the people of the measurement group. We also considered the intention to protect against. Here it was mainly on particulate matter, on air pollution, and this protection intention was studied in the frame of the protection motivation theory that was established by Rogers and Maddox in the 1970s and 80s. And it says that protection motivation is driven by threat appraisal and by coping appraisal. And we see that for all the bold printed factors here, there is a significant impact. So threat appraisal has clearly, all the items here have a very clear association to the protection intentions, and here from the coping appraisal, only the self-efficacy is significant.
Can you say again what protection intentions are?
Yes, protection intention, this is asked by several items in the questionnaire, and I don't have them, but when we meet again, I will tell you. It's like questions: would you next time? Would you choose another way? Or do you think you can protect, or something like this?
You wear a mask, or you maybe.
No, it's just the intention. It's not the real realization of this protection. This is not included. This will come later with the data. But here we just looked for the intention. Are you willing, or would you like to? But nothing more. And another interesting finding is that when we consider the effect of the feedback was given, I think, after the second survey. When we consider the effect of the feedback in the measurement group, only in the measurement group, this is both for the measurement group, the intention to protect against this pollution. Then we split this group in two subgroups with low mobility habits and high mobility habits. And those with low mobility habits, this decreased suddenly after the second. And here we have a sustainable increase of the intention to protect. So far, summarizing this, we just have very preliminary results from our study. we saw that exposure feedback can increase the threat appraisal. Only persons with high coping appraisal can increase their threat appraisal. And carrying the sensors can also increase the protection motivation. But persons with low habits of travel behavior are should be more willing to change their routes. But we saw that this is not a sustainable change, but only for the others who have high habits in their travel behavior. And we are currently actively working on the analysis of all these data, and we would like to do this in collaboration with you and with Kemming. And I'm very grateful that you invited or suggested me to take part here in this fellowship program. And a question that is for me of particular interest, and I discussed this much more in the seminar, I just would like to mention it here, is the region where the individual moves here. For each individual you have a particular region. These are two types of individuals. For example, people who commute from the suburbs to downtown, and the red ones and the green just move around their residence. And the region where they move is called the activity space. And I'm sure that different individuals have different activity spaces. And I wonder whether this is possible to quantify these activity spaces. I'm looking for measures to quantify this. For example, the length of the daily movement. How far will I move every day? Or the number of places I visit every day. And I can imagine that there are many, many more. And I hope that our data are a good basis for some type of machine learning or artificial intelligence to flesh out these patterns. And I believe that the measures of the personal activity spaces are important indicators that can be linked, or that can link the social behavior and the health status and the environmental exposure. I think this is a very interesting vehicle to bring all this together. And to conclude my lecture, I think the time is nearly over, I would like to share some impressions from our last measurement campaign. This is a look at my hometown, Leipzig, where we equipped the volunteers with sensors. And with the sensors, they cycled back and forth between their homes and workplaces and shops and other places, and they explored the urban climate and the air pollution. And in total, we gathered data during 3 years, mainly in summer, because in summer you very often have high pressure with low wind, and so you have strong differences in the different urban regions. But also at other times of the year, and it will be interesting to see this seasonal pattern in the data. Of course, the database has limitations due to missing data. And another issue is that our measurements have a sampling rate of 10 seconds. This is necessary to get sufficient spatial resolution when moving fast with a bicycle. And unfortunately, such measurements cannot be compared with the legal limit values, which are designed for hourly values. So volunteers very often ask us, can you compare my measurements to the legal values, and I am above them or below. And so I would like to thank you for your attention, and I will be happy to answer questions and discuss with you. Thank you.
Thanks so much, Uwe. That was fascinating, and I had several questions that you answered, and then I'm sure we've got questions for you. Anybody got a question for Uwe?
I can start. So extremely interesting. I'm just now trying to translate into something that we economists, right, can make some sense of. So when, for example, we look at risk behavior, risk attitudes, attitude towards risk, and so I was trying. If you can put back the slide, the one where you, yes, the next one. The next one. Yes, this one, right? So exposure, feedback, and increased threat appraisal. So I think that is a concept, threat appraisal. We don't use that, but I think that is a concept to understand that, you know, for example, are you willing to continue with a risky route, or perhaps you want to change that?
Yes.
And that can be measured. This risky attitude can be measured by, for example, how much time and more you are willing to spend on the route, and taking a safer route rather than the dangerous one. In that case, you're risk averse. You can measure risk aversion by looking at the time, extra time that can be employed. So I wonder if you see these changes in route, and that reaching the same destination takes perhaps more time or less. I don't know. Or maybe they continue with the dangerous route, and therefore the most polluting route, and therefore they will arrive more or less at the same time. Do you see this? Maybe over time you follow the same person, then over time you see what can happen, and how this risk perception can change over time as well.
Yes. This is a very complicated point, and we are doing this work together with colleagues who normally develop navigation systems. And they design the navigation system that, for example, when there's a hill or when the street is very poor, then people don't like to walk there or to drive there. So they take this as a criterion for the routing. But now we change this, and we take the air quality and the heat as a criterion for the routing. So, but in the end, this is a combination, and different people will also have different preferences. One individual may choose the fastest lane. The other one may choose the easiest way, not to go uphill or so. And another one would choose the cleanest or the coldest or the most comfortable way. So, but this should be elaborated more, and will be interesting.
Yeah, thanks for a really nice talk. I gather most of your work is focused on daytime.
Yes.
Have you done any work at nighttime?
No.
I asked that because exposure feedback can increase the threat appraisal. It would be very interesting to look at the interaction between the climate fields and exposure and discomfort, so on and so forth, and map those over fields related to personal security. That's a very interesting interaction potentially. Yes. Because a thermally beneficial route may not be a route which is beneficial to your personal security.
Yes.
So I think that's a development.
Yes, thank you.
Quite exciting.
Yes, a good suggestion. To be honest, we did not think about this. We just focused on the daytime and mostly on the rush hour when people very busy and mostly move. And another point is also the indoor conditions. We also did not consider the indoor conditions yet.
And one other thing, most of your work focuses on exposure, which is the stress element. Have you thought about combining it with models of human heat balance, human energy balance, and looking at the response in terms of the strain? Changes in skin temperature, heart rate, so on and so forth. Physiological responses, which measure the strain response to this applied stress.
Yes, this would be also very interesting. So there are also some sensors to measure the skin resistance to register stress. But there's another point that I did not mention, but when you discuss about this here I just considered or discussed about the air temperature, but this is not all. For the UTCI or for the perceived temperature, you have the radiation effect, you have the wind and humidity effect, and all this. But our measurements are too limited. For example, we have no radiation measurements in the personal sensors, and yes. There are limitations.
You need a pyranometer on someone's helmet.
Yes. I can tell you, I had a contact to a colleague in Japan, and he had he developed a very interesting instrument. I'm sure you know this globe thermometer with a white bulb and the black bulb, and he also added a 3 bulb, and this bulb was heated. And when you have the wind, the heated bulb cools down. So you have 3 measurements, and from these measurements you can extract the temperature, the radiation due to the different colors, and the wind. And this would be very interesting. But unfortunately, this is it's in an experimental phase, and you cannot lend this to several children or individuals taking studies in the city.
There was a question at the back and then Ching.
I maybe have 2 points, just like a question of understanding and hold back a little bit on. But on this exposure feedback, please forgive me for being provocative, but why would I need this feedback as an individual, right? The students or your colleagues that were on the bikes, for me it seems to be common sense that the route in the park is nicer, right? And this idea of being nicer obviously goes well together with being less polluted, less crowded, right? With having a nicer scenery. And then I can reduce my exposure to exhausts, right? To the heat, to the noise of the street by just taking the route to the park, right? That might not always be possible, right? So it's like shifting. I know it's like I'm not cycling home when there's a rush hour. I mean, try at least to avoid that in Durham. And the other thing that I wanted to ask, that the exposure feedback, right? I mean, for me, it would be only valuable if you can link the immediate personal danger for me. Because if it's an abstract reduction of now you lost 5 to 10 minutes of your lifespan because you took the more polluted route, if you can even make this attribution, right, then it remains this intangible danger of something that is really where I would say, yeah, okay, where's your issue now? It's not like that you say there's a thunderstorm, please stay inside, because we have gale force winds and lightnings. So I think that, I don't know if that is too provocative, but...
No, this is exactly the question our volunteers ask us as well. What does this mean when I reduce my exposure by such a figure? But as this is not comparable to data that are collected in epidemiological studies and to the legal limit values, we cannot make any conclusion about this. So this is an open question still. And to your first point, I think this is not so easy, because sometimes in the park the air pollution is much higher than on the street. For example, imagine that you have a street and the park, and the wind comes from the west. Then all the pollution goes to the park, and the park is highly polluted, but along the street, on the western side, you have very good air. So for that purpose, I think the feedback is useful, and yeah, it's For sure. We also tried correlations between the perceived exposure and the measured exposure. And for noise, this is very clear because you can hear it. And for heat, it's mostly also very, very clear because you can feel the heat, you can perceive it. But for air pollution, it's not always true. We did not find a clear correlation between the measured and the perceived. Although the person said, oh yes, this is green, it's very nice here and it's very clean, but due to the measurements it was not.
And I think like something that even more complicates it even more is that a relatively healthy person who is able to cycle to university, to its work, office space every day has a very different understanding or perception from the exposure to risk than an elderly person who by default probably would stay inside or trying to rest during noon and where the radiation exposure may be the biggest, and go to bed early or relatively late.
Yes, and this is really true. We had 7-8 years ago, we had a study with questionnaires and about the adaptation behavior, and it turned out that elderly people did not have any stress when it was very hot, because they stayed indoors and they closed everything and this was comfortable. But young mothers who have had to bring their child to the kindergarten and had to go to work, and they were stressed very much by heat. So this is, yes, it depends on the individual situation, how they perceive the stress.
Okay, I think, Jim, if you still have a question? One question and then we'll go for the vote. Thanks. Can
I have a quick one? So thanks for giving this sort of interesting talk. So we learned a lot of different things from modeling and also your sensor development. So because I'm more interested in the modeling side of it, so I like to know you have the temporal model and you also have spatial patterns.
Yes.
What's the link between these two? Maybe I just ask this question and then we'll stop. Well,
definitely, but we have plenty of time afterwards, after Glenn's
so
given
just
the
asking
vote,
this question.
to have a glass of wine together and continue the conversation.
Yeah.
But no,
yes, so just this one. So I want to know about image which you showed about the temporal model and also the spatial pattern which you had.
Yes, I think they just are superimposed, both. You have the daily cycle of the temperature, for sure. On noon it's warmer than in the afternoon, and we cannot identify the spatial patterns when you have this strong daily cycle in this pattern. For that reason, we removed the temporal pattern, and then we identified the spatial cycle. And we will do the same with the sensor data. I think I don't have any sensor data here plotted. But when you have the sensor data, when you measure in the morning and then it's noon and then you take these measurements at different time points and also at different locations, and then when you would like to know, is it at this location warmer than at others, it's difficult to find it out, and for that reason we smooth it, or we smooth the temporal course out, and then we just have these small fluctuations, and they represent the spatial differences. But this we should do to the sensor data. We did not do this so far. But we did some experiments, and it seems another approach would be to have a reference measurement, for example, at the climate station in the city, and then you calculate the differences between these mobile measurements and the reference station. But very often the reference station had also its peculiarities, some small variations, and then this goes into the difference, and you believe that this is peculiarity of the mobile measurements, but really it is not. So for that reason, we intend to smooth the daily course out and just to take some higher frequencies from these measurements.
And I'd like to come in with some thanks.
So, Uwe, Professor Schlink, many thanks for a fantastic talk. This kind of work is incredibly relevant. Not only because of the issue of climate change and having to deal with a warmer atmosphere and possibly a more polluted atmosphere, but also because our cities are developing now at an unprecedented rate. In 2005, we crossed an important threshold with more than 50% of the world's population living in cities. By 2050, it could be as high as 70% of the world's population are living in cities. And many cities are turning into mega cities, cities with populations of over 10 million. And these cities create a huge range of environmental problems. They're noisy, they're dirty, not only in terms of their water, but their air, and they're extremely challenging in terms of the heat they produce. So this kind of work is extremely important and informs our thinking about how we build healthier cities and adapt to what really, in climate terms, is a very harsh climate. Cities have a very harsh climate, and they're quite stressful environments to live in. So thank you for a really stimulating talk. I've got lots of questions in my head. So let's thank Professor Schlink.